In Chapter 1, Part 2, we are going to start by looking at some patterns. So, number 10, we are given Figure 1, Figure 2, and Figure 3 with these tiles. We want to find out what does Figure 4 and Figure 5 look like. So, first I'm going to look at Figure 1 and see, okay, when I go from Figure 1 to Figure 2, what's going on? And I immediately notice that we're adding a block on the top and a block on the side. So think about like adding a block to the first column, and then we're adding one, adding another column at the end. From Figure 2 to Figure 3, we're doing the same thing. We're adding a block here and a block here. So to do Figure 4, I'm going to take my Figure 3, which is right here, and I'm going to add a block at the top. So instead of having 1, 2, 3, 4 blocks, it's now going to have 5 blocks. And then instead of having 1, 2, 3, 4 on the bottom, it's going to have 5. And then to do Figure 5, so again, this is the part that we're adding, I'm going to do the same thing. So instead of 5 blocks here, we're going to have 6. This is going to get kind of messy. And then 6 down here. So this is getting added, and this is getting added. So part B, how does the pattern grow? Well, we are going to be adding 2 blocks or 2 tiles each time. And we can see that with, the visual going from Figure 1 to Figure 2 to Figure 3 to Figure 4 to Figure 5. We're adding 2 blocks. It's increasing by 2. So how many tiles will there be in Figure 0, which is the figure before Figure 1? Explain how you know. So going back to this, if we're adding 2 blocks each time, or 2 tiles each time, we're going to work backwards to Figure 0. So if I add a Figure 0 and I take away 2 blocks, I have 1 block left, or 1 tile. So I'm going to say it's going to have 1 tile. Since we are adding 2 tiles each time, to work backwards, we are going to subtract. So Figure 0 would have 1 block. In problem 11, Angelica is working with these functions, and she wants to find out if she puts in 6 as her input, which one does she have to do first, which one does she have to do second to get an output of 5. So I'm going to start by looking at the first function, which was y equals the square root of x minus 5. So if we plug in 4, we're going to get, 6, we'll have the square root of 6 minus 5, which gives us a 1. If we plug 1 into the second machine, x squared minus 6, so it'd be 1 squared minus 6, that will give us an answer of negative 5. So this is not going to work going in this order. So we'll call this function machine A and this B. So going from A to B is not going to work. Let's go now from B to A. So we'll do y equals x squared minus 6 first, plugging in a 6, so 6 squared minus 6 is 36 minus 6, which is 30. And then plugging into the other machine, square root of x minus 5, so that's 30 minus 5 in the square root, which is the square root of 25, which is 5. So that would work. So we would have to do, I labeled it B, but we're going to have to do the y equals x squared minus 6 first, and then do y equals the square root of x minus 5. So part B, is it possible to find an input that would get a final output of negative 5? If so, how could she do it? If not, explain why not. Well, we did see back in part A that if she did the y equals square root of x minus 5 first, and then did y equals x squared minus 6, she would get an answer of -5. We had talked in class about taking the square root. So if we go back up to this part right here, in part A, we said the square root of 25 is 5. And we said in class that typically we're just looking at the positive answer, but there's also two answers. It's 5 and -5, because -5 squared also gives you 25. So she could also get a final output of -5 by plugging in the input of 6. That would also work. In number 12, we have an input of -9 is put into each of the machines. What is each output? So for A, if we plug in -9, y equals -9 squared plus 3. -9 squared is 81 plus 3, so that would give us 84 for function A. For B, y equals the square root of -9 minus 2. This is a problem. We can't do this at this point. Later in Algebra 2, you'll be able to do something with square roots of negative numbers, but we are going to stop here and say that we can't do it because of the square root of the -9. We can't take care of a negative radical at this point. Part B, Eric wants to get an output of 0. Can he do this with each machine? So what we're going to do is we're going to start by taking the equation x squared plus 3, setting it equal to 0, and solving. So we subtract 3 on both sides. X squared equals -3. Like we saw in the previous problem, we're not going to be able to do anything with this, so this is not going to work. So we can't do square root of -3. So we're going to try the other one, y equals square root of x minus 2. We're going to set that equal to 0. So we're going to add 2 to both sides. Square root of x equals 2. Get rid of a square root, we're going to square, so x is equal to 4. So Eric can do it with the function b, but he can't do it with the function a. We are going to skip to 15, and we're going to look at finding the output when we're given an input. So we're given this graphic here, and we want to find out what is the output when we have g of 2. So when our x is 2. So when you look at the graph, you're going to locate 2 on the x, which is right here, and I see it's located right at 0. So g of 2 is going to be 0. For part B, we're going to do the same thing and find g of -1. So I'm going to locate -1. So it's somewhere around, oops, sorry, that's a little off. If I can erase that. It's around 3, and g of 0 is located at 0. So we're using the graph to identify the input and the output. So g of -1 is 3, g of 0 is 0. And then part C, it says find the input when the output is 1. So now we're looking at the y value for 1, and we're going to go this direction, and we see there's 2, and they're kind of like halfway points. So we're going to say at 2.5 and -0.5, that would be those inputs. So g of -0.5 equals 1, and g of 2.5 equals 1. This last problem that we're going to look at is all about functions, and a function for every input there's one output. So we have this soda machine, and we want to describe the input and output for the machine. So there are two, I'm going to abbreviate here just because I don't have a lot of space. So we're going to say input and output. So there's a button for blast. Blast comes out. Another button for blast. We have S for slurp, LT for lemon twist, and DS for diet slurp. So those are our buttons. Part B, Miss Whitney pushed the button for lemon twister and got a can of lemon twister. She went back, pushed the button for lemon twister, and got a can of blast. Is this functioning consistently? This is going to be a no. Every time that she presses lemon twister, she should get lemon twister. It needs to be consistent. So I'm going to abbreviate LT for lemon twister. She should get lemon twister. When Brandy pushed the top button for blast, she received a can of blast. Her friend Miguel decided to be different and pressed the second button, and he too got blast. Is this functioning consistently? This is going to be yes. When blast, I'm just abbreviate with B, is pressed, blast comes out. When Lutfi pushed a button for slurp, he received a can of lemon twister. Later, Taisha pushed slurp and got a can of lemon twister. They noticed later that every time slurp button was pushed, lemon twister came out. Is this functioning consistently? This is also a yes. So every time the slurp button was pressed, they got lemon twister. And because that happened every single time, it is a function.